Alright, this is a geometry notes. This is section 2.6, notes 14. It says proof statements about segments and angles. Our essential question is, how do you write geometric proof? Well, to do so, you have to use all the logical statements, properties, and postulates to actually prove the geometric proofs. A proof is a logical argument that shows a statement to be true. If it shows it's false, it's not a proof. It's a counterexample. We're going to be using our two-column proofs like we did yesterday, and here's the actual definition. It has numbered statements and corresponding reasons that show arguments in a logical order. Very, very important in a two-column proof that there is an order that actually takes place. And then we're going to be using some theorems, and a theorem is a statement that actually can be proven to be true. Here are our first two actual theorems, so these are given truths. It says that a segment congruency theorem, here, congruency of segments, says that they are reflexive, symmetric, and transitive. So right below it I give you examples that we're going to fill in. And it says if for any segments, if it's going to be reflexive, you're going to have AB with a little line over it will be congruent to AB with a little line over it. They're equal to each other, or they're congruent to each other. Symmetric, like before, still flips things around, so if the segment AB is congruent to the segment CD, well, we're going to flip it, and it says that CD is congruent to AB with the little segment symbols over them. And then on transitivity, same thing taking place as the equality. AB, segment AB is congruent to segment CD, then segment CD is congruent to segment EF. That means I'm ignoring the middle here and going to say that segment AB is going to be congruent to segment EF. Theorem 2, congruency of angles, is basically the same thing as a segment. It's just now dealing with the angles. It says they're both going to be reflexive, symmetric, and transitive. So following the different variations here, examples, for any angle A, the angle A is going to be congruent to angle A. Remember, that's like a reflection. Symmetric has angle A is congruent to angle B, then we're going to flip it. Angle B will be congruent to angle A. And then transitivity, it travels. So I have angle A is congruent to angle B. Ouch. Angle B is congruent to angle C, therefore angle A is going to be congruent to angle C. Alright, if I go into example 1, here's our two-column proof. I've filled in some of our blanks here to try to start helping you out as we start working through these proofs. Here's our picture on the right hand side, and I always write down everything that's given to me. AD is 8, BC is 8, and it says that BC is congruent to CD, and then we're trying to show that AD is going to be congruent to CD. That's what we're trying to prove. That's what has to be our last statement of our proof. Alright, as before, if I look at A, AD equals 8, BC equals 8. This statement always has to start to be your given. Notice it has it there. This is starting out to be your given. Do notice, though, we used the first two, but we didn't use the last one. I want to go ahead and find out where is that step located on my proof. Well, if I do BC congruent to CD, BC congruent to CD, right there on D, that's where it exists, so I'm going to go over here to D and write the word given so that I don't get confused later in my proof trying to figure out what the heck that is. And now, and do not go down to AD and CD and right here on E put prove just because it's there. So many students do that and get it wrong. Alright, here we go. Looking at B. I gotta look at A and B because everything below does not exist. That's the way proofs work. You have to look above to figure out what your reasoning is. So nothing below it actually exists yet. I'm only looking above. AD equals BC. Well, if I look at A, it says AD equals 8 and BC equals 8. Well, these are segments equaling numbers. Segment equaling numbers. What allows us to say that a segment is equal to a number? Well, that's our length of a segment, correct? But it says that AD is equal to BC. Well, if I'm looking at my properties that I had the other day, let me get them just a second. Alright, if I'm looking at my notes from the other day, I have my properties and my reflexive, symmetric, and transitivity. If I'm looking at that, I'm noticing that these are set equal to each other when they both equal an 8. If I'm looking here, I'm trying to figure out which one of these does it actually work for. Most of the time, students will pick segments. Students will pick transitivity because they'll say that AB equals 8 and CD equals 8, then AB must equal CD. Or the fact that AB equals 8 and EF equals 8, then EF and AB equals 8. And that's close. It's not quite right. Because remember, A, B, C, D, and EF are all segments. If I look at my proof, AD and BC are segments, but the number 8 is not a segment. It's an actual number. So this doesn't exist in the same frame. So when these equal numbers, or equal something that is not their same, this is where we are replacing the 8 where the BC is. We're actually replacing this information. Replacing is our substitution. We substituted it for something else. It's our substitution property. Let me go down here and put substitution in our blank. Okay, so we have substitution property of equality. Now on C, I went ahead and filled this in because this has not been told to you yet. That when I go from equals to a congruency, notice this is the same letters, but I went from equals to congruencies with the segment notation above it. This is called definition of congruent segments. When I go from an equals to a congruency. It's something you need to know and take note of. Going from equals to congruence is definition of congruent segments. Now this is my given that I had from above, so it has been used. I'm thankful for that I wrote it down, because otherwise at this point we're going, what is that? Get to my next step, which is my very last step. I'm saying, okay, I've already used this one, I've already used that one. I just used this one saying that they were congruent, so I got them into segments. So if I'm looking at this, I'm saying AD is congruent to CD. If I look at C and D here, it says AD is equal or is congruent to BC, and BC is congruent to CD. Notice I have segment congruent to segment, then that segment repeated is congruent to another segment. So these are all segments. And it's traveling. The AD is congruent to BC, but BC is congruent to CD. So since these repeat, that means AD is congruent to CD. What property is actually following that pattern? Well, if I look back, I'm dealing with segments. I either have reflexive property, I have symmetric property where it flips, or I have transitivity where it travels. A, B, C, D, C, D, E, F, A, B, E, D. So if I'm looking at this one, this is a model of transitivity. And this has a congruent symbol, so this is a transitive property of congruency, and I'm going to put the little symbol for congruence, which is actually up here on our theorem 1. There's our transitivity, congruence of segments. So you can either put transitivity or congruence of segments. Alright, number 2. Name the property illustrated. If I look at the first one, yx is congruent to yz. Yx, yz. Then yz is congruent to pq. Okay, wait a minute. wz, there's wz. Yx, wz, wz, pq. There's something different. Okay, there's something different there. Then it repeats. Yx is congruent to the PQ. What property is that modeling? Okay, and this one is traveling again, so that means this is the transitive property of, and these have congruent symbols, so this is of congruency. If I look at the second example, I have angle M is congruent to angle N, and then angle N is congruent to angle M. So I'm only dealing with two things, and if I'm looking at the pattern, this flipped the order. Something that flips is the symmetric property of, and since I have congruent symbols, this is of congruency. Alright, example 3, here is another proof that we're going to step through. Okay. If I look at what's given to me, it says AD is 12, AB is also 12, BC is congruent to CD, and then AD is congruent to CD. We're trying to prove that BC is going to be congruent to BA. So I highlighted what we're trying to prove. Those two things are supposed to be congruent. Well, let's look at A. AD equals 12 and AB equals 12. What is that? That is our given. Alright, so I used 2 of my given so far. Where's the other parts given? BC is congruent to CD. And AD is congruent to CD. There it is. On F is the second part of your given. So they've got that written down. If I look at my first step, it has AD equals 12 and AB equals 12. So they both equal a number, and then they set them equal to each other. So what property did we just use in the last proof that said when we set segments equal to numbers, we can set them equal to the same thing? Look back at it. Here I had AD equals 8 and BC equals 8, and said they equaled each other, meant that this was substitution. Okay, this is of equals because we have equal signs. Now from B to C, notice I have the same letters, but I changed from equals to a congruent symbol. Equals to a congruent symbol. Look at your last proof. Going from an equals to a congruent symbol, let me slide it up. Equals to a congruent symbol meant that this was definition of congruent segments. Okay. Now look at D. D says AB, segment AB is congruent to BA. AB is congruent to BA. Is that true? Yeah, that's true. It's the same segment. Well, when something's congruent to itself, what property is that actually referring to? When AB equals, or AB is congruent to BA, when it's equal to exact self, just written backwards. If I look back at Theorem 1, dealing with segments, when it's equal to itself, realize this, I can have AB is congruent to BA, and it still be falling under the reflexive property. So this is reflexive. And we're dealing with congruence, so I put the little congruence symbol. If I look at E, they have AD is congruent to BA. I'm looking just ahead of it. Where is that being used? Typically, it's the ones right above it. AD is 2 above. AD is congruent to AB. And then right below it, it says AB is congruent to BA. Well, the BA is right there. So once again, notice these two guys coincide. So I have AD is congruent to BA. BA is congruent to, oh, I said that backwards. AD is congruent to AB. AB is congruent to BA. Therefore, AD has to be congruent to BA. What is that? Okay, what is that when these guys overlap each other? It is transitivity. Okay, so this is transitive property of congruency. Alright, F was our given. So now we're going to be using our given in our next statement. If I'm looking at it, the given says that BC is congruent to CD. Okay. If I look at G, G has the BC being congruent to AD. And on F, BC is congruent to CD. If I look at the next statement, it says AD is congruent to CD. Well, here's CD again. There's CD and there's CD. Both of them have CD. So when they equal, I have BC. And notice here I have AD. Those are both here. So if I'm looking at my pattern, this is being repeated. It looks a little different than up here. These two guys are going together. So if BC is congruent to CD and CD is congruent to AD, then BC must be congruent to AD because this is in both. What is that again? All dealing with segments, and it is traveling. This, once again, is our transitivity. They've just gotten the AD congruent to CD backwards. Looking at the last step, it says BC is equal to BA. Well, I know that BC is equal to AD, so is there anywhere above that says AD is equal to BA? Anywhere above. I look at E. E says AD is equal to BA, which is what I'm needing. So if BC is equal to AD and AD is, congruent. BC is congruent to AD and AD is congruent to BA, therefore BC is congruent to BA. This same pattern, 3 steps, is transitivity one more time. And that's it. Alright, I know these are tough. That's why I'm trying to take them slow. Here's your independent practice. I want you to name what these properties actually are, and we'll discuss them in class tomorrow. Make sure you answer your summary on how do you write geometric proofs.